We are returning to ocean-atmosphere interactions in the context of MJO's interseasonal oscillations again, but now in the context of the model that we looked at with the one baroclinic structure mode in the atmosphere and the ocean with the mixed layer. So it's a very model-specific argument again about what processes are important, but the additional things considered in this model are the feedbacks between SST and clouds and SST and winds. These are empirically found to be very important at MJO timescales, but again, the question is how do you represent it in a simplified model, and how do you interpret it compared to observations, and then how do you go back and look for it in the full GCMs, which don't explicitly have to include these things, but you diagnose the full coupling that's there to see at intraseasonal timescales what are the cloud SST feedbacks in those models and cloud wind feedbacks. And then there is a lot of work recently showing that specific improvements in convection representations like dilute plume approximation. If you don't know what that means, don't worry about it. Convective momentum transport, again, if you don't know what that means, don't worry about it. So those kinds of things are shown to improve the coupling nature of the MJO's ocean-atmosphere interactions and improve certain aspects of the MJOs like propagation speeds and structures and so on. But in this context here, we start with looking at the vertical structure of the MJO. So you have the deep convection here with the shallow congestus on either side, and so you have strong vertical motion here and weaker downward subsidence here and stronger subsidence away from it. So you have the convective complex as we have called it, and there are the shallow cumulus, and all the processes we are looking for exist here. So you have strong easterlies in the upper level and westerlies at the lower level, and in the 850 hectopascal, which you can think of as the top of the planetary boundary layer, there is the westerlies on the western side of the MJO convection and easterlies on the eastern side, and similarly at the lower level, and this is the atmospheric boundary layer. So you have warm and cold temperatures in the atmosphere. You have latent heat flux where we have to consider the impact of the MJO driven winds on the background winds to see where latent heat flux is enhanced to cool the SSTs and create ocean mixed layer response. So you have a deepening of the ocean mixed layer here. Ahead of it you have a weakening of the background winds, assuming they are easterly, which we already said are not easterlies in the Indian Ocean and in the Western Pacific. Nonetheless, this is the kind of model we always use for Vichy and so on. So you have reduced latent heat flux and warmer SSTs and shallower mixed layer here. So now you have feedback from the ocean to the extent that the stronger winds behind not only increase latent heat loss, which we had invoked before, but also you have ocean mixed layer processes where you have entrainment and cooling and deepening. So to deepen the mixed layer you need turbulent kinetic energy, which is cube of the wind speed, and cooling. So you have entrainment of colder water and deepening. So deepening means you're chewing into the colder water below, and so on. So this is the general ocean-atmosphere interaction within which the instability, the growing mode, and the most unstable coupled mode are looked at in this model, which I'm not listing the equations of the model and so on. It's not perfect, it has issues, but here is a schematic diagram that we looked at for the MJO structure, and in B we are looking at the most unstable coupled mode in the theoretical model. Wavy lines denote the surface latent heat flux, which is what we already looked at, and ABL, OML, LHF, WWB, CAPE, and L represent respectively. Atmospheric boundary layer, which you already know here. CAPE is the convective available potential energy. WWB are westerly wind bursts. So those are at a certain synoptic scale with a certain wind speed of 7.5 meter per second, and they last for about a week, and they send off Kelvin waves in the ocean. Can cause remote responses in the ocean ahead of the MJO. And so here, any additional thing we have to look at? So the most unstable mode here is showing again the strong convergence in the free into the deep convection, and you have the strong divergence at the upper level, strong vertical motion, and the subsidence ahead and behind, with the increased latent heat flux and decreased latent heat flux here with the mixed layer response. And the model has a equation for computing H1, the mixed layer depth, in terms of the winds, entrainment, mixing parameterization, and so on and so forth. And this is typically what is done. But in the real full GCMs, whether it's a forced ocean GCM or a coupled GCM, what is not clear is what we talked about before in terms of low frequency rectifications. For example, as I said, the westerly wind bursts associated with the MJOs send off Kelvin waves, and typically westerly wind bursts always produce a downwelling Kelvin wave, which would push the thermocline down, weaken the stratification, and with the same TKE in that case, you can deepen the mix layer and increase the heat content ahead of convection. And if you have multiple MJOs, it's been shown with models that the mean state of the ocean changes. So multiple westerly wind bursts would leave you with, let's say, a deeper mean mix layer at lower frequencies, even at a seasonal time scale. Okay, and that would also show up in terms of chlorophyll response in the ocean, because every time you have entrainment and mixed layer changes, you're entraining nutrients into the euphoric zone where there is chlorophyll blooms. And there is a chapter in the book at the end talking about biological responses, which I'm not going to go into in this series, but that also shows that there are low frequency rectifications associated with these MJO related winds. What do they do in terms of the seasonal variability of the MJOs, or does the MJO that get organized after the first MJO somehow benefit from the signature in the ocean heat content created by the first MJO? Or is that a negative feedback? And all those sorts of questions remain, which we are not getting into here. But there are papers which show that the equatorial Kelvin waves generated in the Indian Ocean hit the coast of Indonesia. I don't know if I have a map. Yeah, so let's say Kelvin waves are generated as the MJO is traveling, propagating eastward, and it's generating waves along the way. Those Kelvin waves go off into the Bay of Bengal and down Sumatra into Java and so on, and there is the Indonesian through flow coming here. Together that generates some interactions here, and baroclinic and barotropic instabilities depending on the season, boreal summer, boreal fall, and so on. Those instabilities then generate waves which can go back and affect the MJO genesis region, and also send off Rossby waves that affect generally the air-sea interactions, vertical structure, and so on here, depending on the season. So when we talk about ocean atmosphere interactions, those kind of things are also important. But in this case of ISO theories, obviously we're only looking at MJO, one MJO, and not the low frequency rectifications and impacts on other MJOs. So to the extent that we are looking at just one MJO, it is clear that the ocean mix layer processes, so ocean dynamics, are involved in the MJO as well as the ocean atmosphere interactions, which we talked about before in terms of just enthalpy exchanges or heat flux exchanges. Okay, so tons and tons of papers are written on this, which means there are still many open questions. So we can just leave it at that and say that the air-sea interactions and ocean-atmosphere interactions are very important for the MJOs, and the critical things to understand still are the cloud SST feedbacks at MJO timescales and cloud wind feedbacks at MJO timescales. And in a modeling sense and prediction sense, we need to understand how the results depend on the representation of those feedbacks. That is model specific, which also means often convective parameterization specific. So people also look at convection permitting models or cloud resolving models. There are some indications that things get better, but fundamental understanding still remains somewhat incomplete. Okay. This kind of concludes the ISO theories part, but there is a summary and conclusion part which I'll come and maybe wrap up in one more podcast. Okay.